Welcome to the Sleep and Learn channel. We invite you to listen to interesting scientific facts that will help you fall asleep gently and, at the same time, learn something new. Relax, close your eyes, and let a calm voice guide you into the world of knowledge and sweet sleep. The diversity of life within the reef. Coral reefs are often described as marine cities. Yet this metaphor only begins to capture their extraordinary biological density. Within the branching corals, over sandy lagoons, and along shadowed crevices lives an astonishing diversity of organisms, from microscopic plankton to large predatory fish. Each inhabitant occupies a niche, contributing to a finely balanced web of relationships that has evolved over millions of years. Reef fish alone represent thousands of species, each adapted to specific ecological roles. Small herbivorous fish, such as parrotfish and surgeonfish, graze continuously on algae that might otherwise overwhelm coral surfaces. Their steady feeding maintains open space for coral growth. Parrotfish, in particular, perform a subtle geological service. By scraping algae from coral rock with their beak-like teeth, they ingest bits of limestone and later excrete it as fine sand. Much of the white sand found on tropical beaches originates from this quiet, repetitive process. Predatory species add further complexity. Groupers and snappers patrol the reef slopes, while moray eels shelter in rocky cavities, emerging at dusk to hunt. Above the reef, swift schools of jacks and barracuda move in coordinated formations, their movements reflecting flashes of silver light. Even larger visitors, such as reef sharks and sea turtles, weave through the ecosystem without disturbing its delicate rhythm. Contrary to popular imagination, reef sharks are generally cautious and maintain a respectful distance from divers. Invertebrates form another vast and colorful layer of reef life. Sea stars, brittle stars, sea cucumbers, and spiny lobsters inhabit the reef floor. Giant clams anchor themselves within coral structures, their iridescent mantles shimmering in shades of electric blue and emerald green. Sponges, among the most ancient multicellular organisms, filter enormous volumes of seawater each day, removing bacteria and organic particles while contributing to nutrient cycling. Among the most fascinating reef residents are the symbiotic partnerships that mirror the coral-algae relationship described earlier. Cleaner wrasses and cleaner shrimp establish cleaning stations, where larger fish pause to have parasites removed from their scales and gills. This interaction benefits both participants and demonstrates the cooperative tendencies embedded within reef ecosystems. Observers often describe these stations as underwater service centers, operating with quiet precision. Reefs also function as nurseries. Juvenile fish seek shelter among branching corals and seagrass beds that border reef systems. The complex architecture of coral colonies provides countless hiding places, reducing predation and increasing survival rates. Many commercially important fish species spend their early life stages within these protective environments before migrating to deeper waters. Even at the smallest scale, life thrives in abundance. Planktonic organisms drift through reef waters, forming the base of the food web. Tiny crustaceans, larvae, and microscopic algae sustain filter feeders and small fish, which in turn nourish larger predators. This layered structure resembles a living pyramid, stable yet dynamic, shifting subtly with tides and seasons. Color plays a vital role in reef communication and survival. Bright patterns may signal toxicity, attract mates, or provide camouflage among similarly colored corals. The clownfish, nestled among the stinging tentacles of sea anemones, gains protection from predators while offering its host nutrients and improved water circulation. Such relationships illustrate how survival in the reef is rarely solitary. Instead, it depends on interconnected cooperation. Sound, too, shapes reef diversity. Healthy reefs produce a constant background crackle created by snapping shrimp and grazing fish. This acoustic environment guides larvae searching for suitable habitat. Studies have shown that young fish are drawn to the subtle symphony of a thriving reef, suggesting that biodiversity is not only visible, but audible. In its full expression, a coral reef is less a single ecosystem than a mosaic of microhabitats: sunlit shallows, shaded overhangs, sandy channels, and deeper fore-reef slopes. Each zone supports distinct communities adapted to light intensity, water movement, and nutrient availability. The result is a layered tapestry of life that remains remarkably stable when environmental conditions are balanced. The diversity within coral reefs reminds us that complexity does not require chaos. Instead, it emerges from countless small interactions repeated over time. In the calm movement of fish schools, the steady grazing of herbivores, and the silent filtering of sponges, the reef demonstrates how cooperation and specialization can coexist in harmony beneath the sea. The ancient origins and geological journey of coral reefs. Coral reefs are not merely ecosystems of the present. They are chapters in a geological narrative that extends back hundreds of millions of years. Long before modern oceans assumed their current form, ancient reef-like structures were already rising beneath prehistoric seas. Fossil evidence reveals that reef-building organisms flourished as early as the Ordovician period, over 450 million years ago. Though the species have changed, the architectural principle, small organisms constructing vast limestone frameworks, has remained remarkably consistent. Early reefs were not always built by corals as we know them today. In distant eras, sponges and extinct groups such as tabulate and rugose corals dominated reef formation. Entire reef systems emerged, thrived, and disappeared during mass extinction events. Each extinction reshaped marine ecosystems, yet reef-building life repeatedly returned, adapting to new environmental conditions. This persistence underscores the evolutionary resilience embedded within reef history. The geological formation of modern coral reefs is closely linked to plate tectonics and volcanic activity. Many reef systems begin around volcanic islands. When a volcano emerges above sea level, fringing reefs may establish themselves along its coastline. Over immense spans of time, the volcanic island can gradually subside due to tectonic movement and erosion. Meanwhile, coral growth continues upward towards sunlight. If subsidence occurs slowly enough, the coral keeps pace, eventually forming a barrier reef separated from the sinking island by a lagoon. When the island finally disappears beneath the sea, a circular atoll remains, a ring of coral encircling open water. This process was first carefully described by the naturalist Charles Darwin during his voyage on the HMS Beagle in the 19th century. Observing reef formations across the Pacific, he proposed that atolls represent the final stage of a subsiding volcanic island. His theory, initially debated, was later confirmed by geological drilling and modern research. Sea level fluctuations have also shaped reef distribution. During ice ages, vast quantities of water were locked in polar ice sheets, causing global sea levels to fall. Many reefs were exposed or damaged during these periods. When glaciers melted and sea levels rose again, coral growth resumed on newly submerged continental shelves. Thus, modern reefs often rest atop older, buried reef structures, layered records of changing climates. The limestone skeletons that compose reefs are not static stone. They are dynamic geological materials. Over time, waves, storms, and biological erosion break fragments from coral frameworks. These pieces accumulate as coral rubble and sand, contributing to the formation of tropical islands and beaches. Entire low-lying island nations owe their existence to the slow accumulation of reef-derived sediments. Chemical processes further influence reef geology. The ability of corals to build skeletons depends on the concentration of carbonate ions in seawater. Variations in ocean chemistry over geological time have altered how efficiently reefs could form. Periods of favorable chemistry correspond to reef expansion, while less favorable conditions coincide with reduced growth. Storms and cyclones, though seemingly destructive, play a paradoxical role. Powerful waves may break apart coral branches, yet these fragments can reattach and grow elsewhere, contributing to reef renewal. In this way, disturbance becomes part of the reef's natural cycle, reshaping its structure while maintaining overall continuity. Reefs also act as geological archives. Massive corals lay down annual growth bands, similar to tree rings. Scientists can analyze these layers to reconstruct past sea temperatures, salinity levels, and even historical storm frequency. Within their calcium carbonate skeletons, reefs quietly store centuries of environmental data. Viewed through a geological lens, coral reefs are both ancient and contemporary. They arise from biological activity, yet endure on timescales associated with mountains and continents. Their existence depends on delicate ecological relationships, but their structures record the vast movements of Earth's crust and oceans. In their layered limestone foundations, coral reefs remind us that life and geology are not separate domains. Instead, they are intertwined processes, small living organisms shaping vast physical landscapes over immeasurable spans of time. The future of coral reefs and the role of human stewardship. The future of coral reefs rests at the intersection of natural adaptation and human responsibility. These ecosystems have endured climatic shifts, sea level changes, and geological upheavals for millions of years. Yet the speed and scale of modern environmental change present challenges unlike those of the distant past. Understanding the future of reefs therefore requires examining both ecological processes and the evolving relationship between humanity and the ocean. Climate change remains the most significant global pressure. Rising sea temperatures increase the frequency of coral bleaching events, while ocean acidification alters the chemistry necessary for skeleton formation. However, research conducted across tropical regions has revealed that not all reefs respond identically. Some coral communities exhibit partial resistance, and certain species demonstrate genetic traits associated with heat tolerance. Scientists are studying these resilient populations to better understand how adaptation might unfold in coming decades. Marine Protected Areas, MPAs, have emerged as one of the most effective conservation tools. By limiting fishing pressure and coastal development within designated zones, MPAs allow ecosystems to maintain higher biodiversity and stronger ecological interactions. Healthy fish populations, particularly herbivores, help prevent algae from overwhelming coral surfaces after disturbances. In this way, protection strengthens the reef's natural capacity for recovery. Technological innovation also plays a growing role. Satellite monitoring and underwater sensors now track sea temperature, acidity, and reef health in near real time. These data allow researchers to anticipate bleaching events and respond with targeted management strategies. Advances in coral aquaculture enable the cultivation of heat-tolerant strains in controlled nurseries, which can later be transplanted to degraded areas. While such interventions cannot replace global climate solutions, they may enhance localized resilience. Coastal communities are essential partners in stewardship. In many regions, traditional knowledge has long guided sustainable fishing and reef management practices. Integrating scientific research with local expertise fosters conservation approaches that respect both ecological and cultural continuity. Education initiatives further support this collaboration, encouraging sustainable tourism and reducing pollution from land-based sources. Economic considerations are equally significant. Coral reefs contribute billions of dollars annually through fisheries, tourism, and coastal protection. Recognizing their economic value strengthens arguments for conservation investment. When communities perceive reefs not merely as scenic landscapes, but as vital infrastructure, protective measures gain broader support. At the same time, reducing greenhouse gas emissions remains central to long-term reef survival. Global climate stabilization efforts directly influence ocean temperature trends and acidification rates. While reef restoration can assist recovery, preventing excessive warming addresses the root cause of widespread bleaching. Thus, local stewardship and global policy are interconnected dimensions of reef conservation. Encouragingly, case studies from various tropical regions show that reefs can rebound when stressors are minimized. Areas where overfishing has declined and water quality has improved often display increased coral cover and fish abundance within a decade. These examples demonstrate that resilience is not theoretical. It is observable when conditions allow. Public awareness continues to expand as underwater photography and documentary filmmaking bring reef ecosystems into global view. Images of luminous coral gardens and diverse marine life inspire both admiration and responsibility. The visual beauty of reefs often becomes a catalyst for conservation engagement, bridging emotional connection with scientific understanding. The future of coral reefs will likely differ from their past. Species composition may shift, and certain regions may become more dominant than others. Yet, change does not necessarily imply disappearance. Ecosystems adapt, reorganize, and evolve. Human stewardship can influence whether this transformation preserves biodiversity or accelerates decline. Ultimately, coral reefs illustrate a broader principle. The health of marine systems reflects the cumulative impact of human choices. By safeguarding water quality, managing fisheries sustainably, and addressing climate change, society participates directly in shaping the trajectory of these underwater worlds. The living architecture of coral reefs. Coral reefs are among the most intricate and visually captivating ecosystems on Earth. Often described as the rainforests of the sea, they occupy less than 1% of the ocean floor, yet they support approximately a quarter of all known marine species. Their quiet complexity unfolds beneath clear tropical waters, where sunlight filters down in soft, wavering beams and illuminates vast underwater cities built not of stone, but of life. At first glance, corals resemble colorful rocks or underwater plants. In reality, each coral structure is formed by thousands, sometimes millions, of tiny animals known as polyps. A single polyp is a soft-bodied invertebrate related to jellyfish and sea anemones. It secretes a hard outer skeleton made of calcium carbonate, which gradually accumulates over generations. As colonies grow and new polyps build upon the skeletal remains of their ancestors, reefs slowly expand upward and outward, forming barriers, atolls, and fringing formations along coastlines. The pace of reef growth is patient and unhurried. Some massive coral species may grow only a few millimeters per year, while branching varieties can extend several centimeters annually. Over centuries and millennia, these incremental additions create structures large enough to be visible from space. The most famous example, the Great Barrier Reef, stretches for more than 2,300 kilometers along the northeastern coast of Australia, making it the largest coral reef system on the planet. Coral reefs thrive primarily in warm, shallow waters between 23 degrees north and 23 degrees south latitude, a region often called the tropical belt. Their reliance on sunlight is not incidental. Within the tissues of most reef-building corals live microscopic algae known as zooxanthellae. This relationship is a striking example of symbiosis. The algae perform photosynthesis, producing nutrients that feed the coral host, while the coral provides shelter and access to sunlight. The brilliant colors associated with reefs, luminous greens, warm golds, delicate pinks, and deep purples, are largely due to these microscopic partners. Beyond their biological beauty, coral reefs act as natural breakwaters. Their limestone frameworks absorb and dissipate wave energy, reducing coastal erosion and protecting shorelines from storms. In many tropical regions, entire communities depend on reefs for fisheries, tourism, and cultural heritage. The reef's calm lagoon waters, sheltered by outer reef barriers, often provide safe anchorage and nurseries for marine life. Reefs form in three primary structural types. Fringing reefs grow directly along coastlines, separated from shore by narrow lagoons. Barrier reefs lie further offshore, divided from land by deeper, wider lagoons. Atolls, circular or ring-shaped reefs surrounding a central lagoon, typically form around subsiding volcanic islands. As an island gradually sinks over geological time, coral growth continues upward towards sunlight, eventually leaving only the ring-shaped reef as a trace of the vanished landmass. Despite their apparent solidity, reefs are dynamic systems. They pulse with daily rhythms, polyps extending delicate tentacles at night to capture plankton, fish weaving through coral branches at dawn, and subtle chemical exchanges occurring invisibly within the water column. Even in stillness, there is motion. Even in silence, there is life. Perhaps the most relaxing aspect of coral reefs lies in their slow continuity. Individual coral colonies can live for decades or centuries, while reef systems themselves may persist for millions of years. They are records of environmental history, layered in limestone, quietly documenting shifts in climate and sea level over vast spans of time. In their gentle balance between fragility and endurance, coral reefs embody a paradox. They are both resilient architects of the ocean and delicate communities dependent on precise environmental harmony. Understanding their foundations, the living polyps, the patient accumulation of skeletons, and the luminous partnership with algae, is the first step toward appreciating the deeper stories woven through these underwater worlds. The subtle balance between fragility and resilience. Coral reefs exist in a delicate equilibrium, sustained by precise environmental conditions. Warm, clear, sunlit waters provide the energy necessary for coral growth, yet even slight deviations in temperature, salinity, or water chemistry can disrupt this balance. This sensitivity often leads to the perception that reefs are fragile. Yet alongside this vulnerability lies an equally remarkable capacity for adaptation and recovery. One of the most visible expressions of stress is coral bleaching. When sea temperatures rise beyond a tolerable threshold, corals expel the symbiotic algae living within their tissues. Without these algae, the coral's translucent body reveals its white calcium carbonate skeleton beneath. Although a bleached coral is not immediately dead, prolonged stress can lead to mortality. Bleaching events, once rare, have become more frequent in recent decades due to warming oceans. Despite this vulnerability, resilience emerges in unexpected ways. Some coral species demonstrate higher tolerance to temperature fluctuations. In certain regions, reefs exposed to naturally variable conditions, such as shallow lagoons with daily heat swings, appear better adapted to withstand thermal stress. Over generations, natural selection may favor corals capable of surviving warmer waters, gradually reshaping reef communities. Reefs also possess intrinsic regenerative abilities. When storms break coral branches, fragments can reattach to stable surfaces and continue growing. This process, known as fragmentation, allows reefs to recover structure after disturbance. Similarly, fish populations often rebound when fishing pressure decreases and habitats remain intact. The interconnected web of reef life supports cycles of renewal, provided foundational conditions remain stable. Human communities are increasingly participating in reef restoration. Scientists cultivate coral fragments in underwater nurseries, where they are protected during early growth stages. Once mature enough, these corals are transplanted onto degraded reef areas. Such efforts do not replace natural processes, but aim to assist recovery where environmental stress has been reduced. Restoration highlights a collaborative dimension between human stewardship and ecological resilience. Water clarity plays a crucial role in maintaining reef health. Excess sediment from coastal development or river runoff can block sunlight, limiting photosynthesis within coral tissues. When sedimentation is controlled, reefs often show significant improvement. This responsiveness underscores the fact that reef systems, though sensitive, can recover when stressors are minimized. Biological diversity itself strengthens resilience. Reefs with a wide variety of coral species and fish communities tend to withstand disturbances more effectively. Herbivorous fish help prevent algae from dominating damaged areas, creating space for coral larvae to settle. In this way, biodiversity acts as a stabilizing force, buffering the ecosystem against sudden change. Ocean chemistry adds another layer of complexity. As atmospheric carbon dioxide dissolves into seawater, it alters carbonate availability, the building material corals require for skeleton formation. While this chemical shift presents challenges, research indicates that some coral species can adjust growth strategies, allocating energy differently to maintain skeletal development under changing conditions. Time remains a critical factor in resilience. Reefs have endured natural climate fluctuations for millions of years. Their fossil record reveals cycles of expansion and contraction, extinction and renewal. What distinguishes the present era is the accelerated pace of change. Yet within living reefs today, one can still observe adaptation unfolding. Larvae settling on newly available surfaces, tolerant species expanding their range, and ecosystems reorganizing in response to shifting conditions. The balance between fragility and resilience is not a contradiction, but a dynamic relationship. Coral reefs are sensitive precisely because they operate near optimal environmental thresholds. This sensitivity enables high productivity and biodiversity. At the same time, their evolutionary history equips them with mechanisms of survival that have persisted across geological epochs. To contemplate a coral reef is to witness both vulnerability and endurance intertwined. Its beauty depends on balance. Its future depends on the preservation of that balance. In the gentle sway of coral branches and the steady return of fish after disturbance, resilience reveals itself not as dramatic resistance, but as quiet persistence. The gentle rhythms and hidden signals of the reef. Coral reefs are not only places of immense diversity, they are also environments governed by rhythm. Beneath the surface, life follows patterns shaped by light, tides, lunar cycles, and seasonal change. Though the reef may appear still to a distant observer, it is in constant motion, breathing, feeding, communicating in ways that are subtle, yet remarkably coordinated. One of the most fascinating rhythms is the daily transition between day and night. During daylight hours, many reef fish are active, grazing and navigating the bright coral landscape. As dusk approaches, the character of the reef transforms. Diurnal species retreat into crevices, their colors fading in the dimming light, while nocturnal creatures emerge. Sea urchins begin their slow crawl across the reef surface. Brittle stars unfurl their arms, and predatory fish move with heightened sensitivity through the darkness. Coral polyps themselves follow a nightly routine. While they rely on symbiotic algae for energy during the day, many species extend delicate, translucent tentacles at night, to capture plankton drifting in the current. In the beam of a diver's light, these tentacles resemble miniature forests, swaying gently in invisible tides. This feeding behavior demonstrates that corals are not passive structures, but responsive animals, finely attuned to environmental cues. Tides further influence reef life. As ocean levels rise and fall, water flow shifts nutrients and oxygen through the reef's complex architecture. Incoming tides often bring plankton-rich waters that stimulate feeding, while outgoing tides carry away waste products. Fish adjust their positions accordingly, seeking areas where currents provide both food and shelter without excessive turbulence. Perhaps the most extraordinary rhythm of all is synchronized coral spawning. Once each year, often shortly after a full moon, many coral species release billions of eggs and sperm into the water simultaneously. The sea becomes briefly filled with tiny floating spheres, rising toward the surface in a silent, luminous cloud. This mass event increases the likelihood of successful fertilization and reflects an astonishing level of biological timing linked to lunar cycles and water temperature. For a few nights, the reef participates in one of the largest reproductive events on Earth. Sound also plays a role in reef rhythms. Healthy reefs produce a continuous background crackle created by snapping shrimp and the scraping of feeding fish. These subtle sounds travel through water and act as orientation signals for larvae drifting in the open ocean. Research has shown that juvenile fish can detect these acoustic signatures and use them to locate suitable habitats. In this way, the reef quietly calls future generations home. Light variation shapes reef behavior in equally intricate ways. In shallow waters, shifting wave patterns create moving mosaics of brightness across coral surfaces. Fish adapt by changing coloration or positioning themselves within shadowed overhangs to avoid predators. Some species possess reflective scales that scatter light, making it difficult for hunters to isolate a single target in a shimmering school. Seasonal changes bring longer-term rhythms. Variations in water temperature and nutrient availability influence growth rates, reproductive timing, and species composition. Even subtle shifts in ocean chemistry can alter how efficiently corals build their calcium carbonate skeletons. Over decades and centuries, these seasonal patterns accumulate, leaving faint growth bands in coral structures, natural archives of environmental history. Despite these continual movements, the reef maintains an impression of tranquility. Its rhythms are gradual rather than abrupt, cyclical rather than chaotic. Life expands and contracts, brightens and dims, feeds and rests, all within a framework shaped by predictable natural forces. To observe a reef closely is to witness time expressed in layers. Minutes measured in feeding cycles, months in reproductive events, and centuries in skeletal growth. These gentle rhythms, repeating across generations, create a sense of continuity that feels both ancient and enduring.